Hello everyone, my name is Anil Rizaoglu. Currently, I'm a senior student in Department of Electrical and Electronics Engineering in Bilkent University. And here is my course project called PSIF sequences in magnetic resonance imaging. It's a course project about the course which is whose name is Fundamentals of Magnetic Resonance Imaging, and this is Spring 2016. So here how my outline goes. First of all, I will be starting with introduction, and um, so as you recognize, I didn't give the full version of the name of the fast because I just give the abbreviation right now, which is PSIF. So in the introduction part, I will talk a bit about the naming of the pulse and then the history of this pulse sequences. And then for the sake of completeness, I will give the pulse structure, I mean the X, Y, Z gradient mechanisms and how we read out and RF pulses are oriented in the time domain. And the reason that I didn't give the full version of the abbreviation at the beginning of the presentation is that the name of the pulse sequence PSIF doesn't have any meaning itself. Uh, However, it's a reverse form of FISP, which is a special type of pulse sequence, and it's a primitive version of PSIF. That's why I thought that it would be really intuitive and it will provide a good foundation in order to understand the advanced concept in PSIF. That's why I will be introducing the primitive version of this pulse at the beginning, and then I will switch to PSIF. And the signal intensity equation is also another important component, and I will mention about the T2 dominated images under the effect of the pulse sequence. And of course, there are a little bit technical issues that we had to deal with during the implementation of this pulse process. And those are the reasons that this pulse sequence is not commonly used in today. And then I will be talking about the application fields of this pulse sequence and what kind of tissues can be imaged by using that. So firstly, introduction, PSIF, as I said, the abbreviation doesn't stand for anything, but it is a time reverse form of FISP. FISP means fast imaging with steady state free precession, and it was invented before PSIF, and that's why once PSIF is um, introduced, then they didn't name it differently, but they just thought that since the PSIF is just the mirror image in the time domain of FISP, then we can just reverse the abbreviation and we can use it for naming another particle. So the abbreviation itself doesn't have any meaning, but it's the reverse form of FISP. So PSIF is a specific name of for Siemens products, but GE and Toshiba names it differently. They rather call both of them PSIF and FISP. They call them SSFP. SSFP stands for steady state precession, free precession, which is a bit misleading abbreviation, but it is okay because they both show the feature of SSFP. And the Philips name is as T2FFE. FFE stands for, as we all know, fast field echo. Actually, gradient echoes are called field echoes by Philips. So one can see different names on the web when she's searching for PSIF. The important thing about PSIF pulse signals is that um, it's a echo-based imaging. I mean, we are imaging the rephasing of an echoes rather than free induction decay. That's why gradient echoes plays an important role in the imaging procedures. I will be talking more about this issue on the upcoming slides. So pulse structure, like pulse orientation of the PSIF sequence. Um, So as I mentioned in the previous slide, the important part is that the echoes of PSFI sequence uh, are caused by RF pulses from the previous cycle. In other words, um, in the previous period, RF pulses are the main reasons for this period's PSIF echoes. And that's why the effective echo time for our pulse sequence is TR plus TE, because in order to see the effect of, to be able to see the effect of RF pulse in the previous cycle, we have to wait TR time, and TE is our conventional time duration that has to be passed. That's why TR plus TE is an effective echo time for this pulse sequence, and residual transverse magnetization is conserved because of the RF pulse structures. FISP, the main reason of introducing FISP's concept is that, as I said, it's the primitive version of PSIF, and it would be really intuitive to understand what's going on with FISP so that we can understand, we can have general idea about PSIF. So um, this is the signal equation, signal intensity formula for FISP. The balance gradients refocus both components at the exact center of PR intervals, and they're doing it as a single echo. So this pulse structure has different names, and one of the well-known names is Fiesta, which stands for fast imaging employing steady state acquisition, and as it was the case for PSIF, Philips and other well-known MRI firms, MRI producing firms, call their own versions. And for most true FISP applications, T2 over T1 images are desired, and that's why repetition time is chosen as short as possible. So once we understand the basic of FISP, then we can switch back to our original topic, which was PSIF, which is the reverse version of FISP in time domain. So our signal intensity equation can be seen here. So one thing to recognize here is that relatively large evolutionary period before echo collection. Um, so because of this relatively large period, actually we can observe a natural decay in the transverse domain. So rather than seeing the effect of T2 star, T2 star is a decay caused by field irregularities and etc. Since we're using echoes, what we are seeing is effectively T2 decay, and that's why the image that we acquire are kind of images which is weighted by T2 rather than T2 star. That's why it's a prominent way of T2 star weighting, and the images show the T2 star orientation is the cross-sectional image of a head, coronal image, yes. And there are a little bit technical issues with the pulse sequence. Generally, what we are trying to do is to suppress fat as much as possible, and in PSIF, fat suppressed image usually provide better nerve to background contrast ratio, and due to the steady state nature, the low diffusion moment, there's a adequate suppression for vascular signals, and in order to get most time efficient results, we have to use the coronal or sagittal planes, and there are published papers in 2014 and 15 regarding with the time efficient imaging of PSIF pulses. And application fields are also lastly the topics that I would like to mention. So PSIF sequences are generally useful for displaying the high signals from fluids uh, like CSF fluids. And in the 1990s, it was a pretty the similar type of applications were really popular. Uh, However, in today, PSIF is not really commonly used type of pulse sequence because of the fast spin echo and balanced GLE sequences. And some recent publications suggested that with modifications, they may be useful for peripheral neurography and diffusion imaging, and also black blood angiography. So these are the possible application fields. And also one should note that there is still ongoing research potential, especially in the imaging of fluids and CSF by using PSIF pulse sequences. And here are my references.